These are the activities for College Algebra Lesson 32. Number 1, we're going to start with this chart that measures population growth for several different countries, and we want to fill in all the missing information. Okay, so let's look. We have the United States as our first country to investigate. The 2010 population was 309.6 million, and my annual growth factor here is given, 1.00969. So if we know the growth factor, we can calculate the continuous growth or decay rate by taking the ln of the growth factor. Okay, so this is my B column. My K column is always just ln of B. So I'm going to take the ln of 1.00969. I'll write it out for this first one. And that comes out to approximately 0.0096. And then now that I know both B and K, I can create models using A naught times B to the T or A naught times E to the KT. So A naught times B to the T, my A naught is my 2010 population, and then times B, which was given, raised to the T. And then for A naught E to the KT, I'm going to have F of T equals A naught, which is still 309.6, times E, and K we decided was 0.0096 T. Okay, looking at Liberia, I have an initial population of 4.1, and my growth decay factor is 1.035. So I'm going to take the ln of 1.035, and I get 0.034 as my continuous decay rate. And then I can plug the values I have into these two models. So F of T would be 4.1 times B, which is 1.035 to the T, or 4.1 times E to the 0.034 T. Okay, Qatar, very similar. 1.112, I'm going to take the ln of that to get my continuous growth rate, and I get 0.106, and then plug into both of the models. So A naught is 1.7, B was given 1.112 to the T, and then for the continuous growth model, I have 1.7 E to the 0.106 T. For China, I have the initial population, and instead of giving the growth factor, they gave me the continuous growth rate. And if I want the growth factor, I do E to the K. So I have K, I just do E to this number, and I'll get B, my growth factor. So E to the 0.00499 is 1.005. And I already have written the continuous growth model. The periodic growth model would be initial value, 1338.1, times the growth factor, 1.005 to the T. Guatemala, initial value is given 14.4. I'm going to do E to the K. K is given, so E to the 0.02469, and that gives me 1.025. And now I can write both models. So I have 14.4 times B to the T, or 14.4 E to the KT. And finally, we have Germany, which has a negative decay rate, which means that the population is shrinking, which means that this should be a decay factor, meaning it should be less than 1. So let's double check. I'm going to do e to this value, e to the negative 0.002, and I get 0.998 as my growth or my decay factor. So now I'm just going to plug into my two formulas. So I have A naught times b to the t, and then I have A naught e to the kt. Okay, next I want to label each of these graphs and match them to the country graph of its population model. Okay, so I'm going to start by looking at y-intercepts. There's a couple of them that stand out. These all look very, very close to each other, so it's going to be tough to decide which ones these are, but this one and this one look pretty clear. The very largest initial population was China with 1338. So this graph is China. And then this initial population looks like it's around 300 or for 300 million, which was the United States. Okay. This graph is growing the fastest. Okay, it doesn't start very big, but it's growing very, very fast. Which country was growing the fastest? If you go back and look at the table, you'll see that Qatar was growing the fastest. Okay, only one of the countries in my table had a decreasing population. It was decreasing very slowly, like a negative 0.002 was the decay rate. So only one of these graphs is decreasing, and it's this one. That looks like an initial population of about 80, which Germany was about 80 million, somewhere around there. And it looks like it's constant rather than decreasing, but that's just because this scale is very big in order to fit all these countries on it. It is actually decreasing very, very slowly. So this one is Germany. And I have two left. One is growing faster than the other. So this one is growing faster than this one. So their initial populations are too close together to be able to tell which one is which using the y-intercept, but I can look at the growth factor. So of the two remaining countries, which one has a faster growth rate? And so when I go back and look at the table, Liberia had the faster growth rate. It started smaller than Guatemala, but it's growing faster, so it will eventually gets bigger. So this one is going to have to be Liberia. And then Guatemala is the final country. It started with a population greater than Liberia, but it's growing slower. So eventually Liberia overtakes it, and this graph is now Guatemala. Next, I want to use the graph to estimate the year when the population of Qatar will equal China. So when the two intersect is right here. I can just draw a line down to the x-axis, and that looks like, I don't know, maybe 65 years. So after approximately 65 years, after my initial year was 2010, so 2075. So Qatar's land area is 4,468 square miles. It's comparable to about Connecticut, while China's land area is 3.7 million square miles. So do we think that Qatar's model with an annual growth factor of 1.112 is sustainable? No, we cannot fit, even China's current population could not fit into Qatar, especially not 1,900 million people. Number 3, the growth model A of t equals 107.4 e to the 0.012t. describes Mexico's population in millions T years after 2006. What is Mexico's continuous growth rate? That is the K value in the e to the KT formula. So this is just read it out of the formula, 0.012. And how long will it take Mexico to double its population? Well, it initially starts with 107.4 million people. And if I double that, that would be 214.8. So I'm going to take my 107.4 e to the 0.012 t and set that equal to 214.8. And I'm going to be solving for t. The question is how long will it take? So it makes sense that I'm solving for time. I'm going to start by dividing both sides by 107.4. So I get 2 equals e to the 0.012 t. Then I'm going to take the ln of both sides. So the ln of 2 equals 0.012 t, because the ln of e to some stuff just gives you the stuff. Ln and the natural exponential function are inverses. And then just divide both sides by 0.012. So t is the ln of 2 divided by 0.012, and that comes out to approximately 57.8 years. Number 4, polonium-210 has a half-life of 140 days. Suppose a sample of this substance has a mass of 300 milligrams. Find a function of the form a of t equals a naught times b to the t that models the mass remaining after t days. All right, so I'm going to start by saying my initial value is 300, and I'm having it every 140 days. So I can't just put a t up there because that would mean I have it every day. It halves every day, but it halves every 140 days. So what I need to do is take my number of years and divide by 140. That will tell me how many sets of 140 days have passed, and thus how many times I need to have my initial quantity. And then if I want to simplify this so that it looks like a naught times b to the t, I could say this is 300 times 1/2 to the 1 over 140 all raised to the t, and that'll give me my b value. So I have 300 times 0.995. Okay, so that is acceptable. This is also acceptable. Now I want to find a function of the form a naught e to the kt that models the mass remaining after t days. Okay, so k is the ln of b. I know b is 0.995. So I'm going to take the ln of 0.995. I'm not going to cut off the decimals. It's 0.995061185. And that gives me about negative 0.00495. And then I can plug that into my other formula. A of t equals a naught, which is 300, e to the negative 0.00495 t. Use either form of the function to find the mass remaining after 1 year, or 365 days. So I'm going to use my original form, the first one I wrote down, 300 times 1/2 to the t over 140, and then I'm going to plug in 365 for t. Okay, so 365 over 140 is 2.6 and change. So I'm going to do 1/2 to that power, and then times 300. I'm not rounding anything while I'm doing this work in my calculator. And I get equals 49.237 or 0.24. Now I'm going to round at the very end. I'll put an approximate here because I rounded. 0.24 milligrams. Now I can use either form of the function to find out how long it will take for the sample to decay to a mass of 200. So maybe I'll use the other form to answer this question, just because I can pick whichever one I want, this one or this one or this one. Okay, so I'm going to write out the form. A of t equals 300 e to the negative 0.00495 t. And then I want to know how long, so I'm going to be solving for t, for time, till I get 200. So I'll make 200 the left side. Divide both sides by 300, and I have 2/3 equals e to the negative 0.00495 t. And then I'm going to take the ln of both sides. So the ln of 2/3 equals negative 0.00495 t. Divide both sides by negative 0.00495, and I get t is approximately 81.9 days. Number 5, logistic growth models. In our earlier examples of exponential growth, we assumed a population grew by the same percentage each time period, but in most growth situations, indefinite exponential growth is not realistic. Growth is always limited because of limited space and resources. In reality, the growth rates of populations will start to decrease and level off and approach a maximum level. So this would be a horizontal asymptote, as resources, space, and other needs decrease. So the logistic growth model is used to capture the long-term behavior of a growing population in a closed environment, and it looks like this graph. So it starts out looking exponential. It grows quickly, looks like an exponential function, but then it starts to slow down and level off towards this horizontal asymptote, sometimes called the carrying capacity of the environment. So the mathematical model for logistic growth is this formula, f of t equals c, so c is just an unknown constant, over 1 plus a e to the negative bt. And a, b, and c, those are all numbers. And it will always give a graph that sort of has this shape. And as t goes to infinity, the expression a e to the negative bt is going to go to 0 because that is exponential decay. Okay, so that means that this expression is going to 0. So 1 plus 0 is 1. C over 1 is C. So that means I do have an asymptote, a horizontal asymptote at y equals C. So an example would be to model the spread of the flu with a function f of t equals 30,000 over 1 plus 20e to the negative 1.5 t, where t is time in weeks. So how many people became ill with the flu when the epidemic began? So that would be time 0. So I'm going to evaluate f of 0, and that would be 30,000 over 1 plus 20e to the negative 1.5 times 0. And that would be 30,000 over 21, which is about 1,429 people. How many people were ill by the end of the 4th week? So after 4 weeks, I'm just going to plug a 4 into my formula and see how many people were ill. And I'll just have my calculator do this for me. I get approximately 28,583 people. And what is the limiting size of the population? It's always this number on top, the C. So it's 30,000. And we can confirm all this in the graph. So f of 0 would be the y-intercept. right here, it does look like, it's hard to tell with the scale that I've given, but it does look like it's, you know, well below 5,000. It could be around 1,500, 1,429. And then f of 4, if I go up to my graph at x equals 4, t equals 4, it's about right here. That definitely looks like it could be at 28,583. And then my asymptote, when I look at the graph, does look like it's at 30,000.